All right. Good morning, students. How was your night? I'm the next person taking over in your chemistry 102, and I hope you will have a swell time together. The most important thing here today is you to be attentive so that you can have a good understanding of it. I am Holaolu Agunkunle by name, and I'll be taking you in the chemistry of groups 3, 4, and 5 elements. As you can see on this slide, group 3 elements, 4 and 5 elements are very unique. But I'm not going to go into teaching you this until you have a good understanding, of what they are all about. I don't know whether this is the overview of what I'll be teaching you. I don't know if you have an understanding of stability, electronic configuration. At this level, I expect all of you to know how to write the comprehensive electronic configuration of elements 1 to 30. Don't stop at 20. In your secondary schools, you were encouraged to stop at element 20. But in this university, for beginners, you have to know the first transition series. Knowing the first transition series is not even enough. You must be able to write them and actually know how the ions can be formed. I can write here. Okay. I will try my best possible to indicate how this can be done. It's a pity I can't see you face to face, but I can see that quite a number of you are here already. Look at the overview. We want you to look at the different types of periodic table. There are a series of periodic tables that are existing, that are in existence, but there are some that are categorized as the standard ones. The IUPAC periodic table is about the best that we are going to use as the standard, but the most commonly used is the Roman periodic table. Let me give you a typical example of a periodic table. I hope you can all see this. This is the typical representation of our periodic table. I know that you can see these groups and then you can know the categories. For instance, if you look at groups 1 and 2, they are the S block elements. What characterizes the S block elements? They are usually metals. And when you write the electronic configuration, you will see that their outermost electrons are in the S orbital. Let's take, for instance, pick sodium. I know that you know that the atomic number of sodium is 11. Let's write its configuration. 1s, 1s2, 2. All right. 2. Let me start afresh. 1s2, 2s2, 2p6. When you add all this together, how do I erase this? 2p6. Okay. 2p6, and then you have a 3s2. Looking at this configuration, you will see that the outermost electrons of sodium are in the s orbital. That is why it is categorized as what? As an s block element. It goes, if you look at elements 13, 14, 15, 16, and 17, those are the ones categorized as the p block elements. And 18, you will see that the p block elements, if you write the electron configuration, the outermost electrons will be what? In the p orbital. And then they have different characteristics. The s block elements are what? Are metallic in nature, while the p block elements are non-metallic. It's a combination of metalloids and non-metals. When you have, I hope you understand what we mean by metalloids. When you were taught your group 1 and group 2 elements, they must have extensively taught you of how to deal with these entities. Metals are usually what? Are they reducing or oxidizing in nature? Do they gain electrons or lose electrons? You must always know that metals are usually electron deficient species, while non-metals are electron rich species. But how did this come into play? In your textbooks, in your past textbooks, you must have seen some other periodic table. we have the Arabic periodic table, and then we have the Roman periodic table. The Roman periodic table is the most common until the IUPAC took it up. Because of the series of these periodic tables, that was when the International Union of Pure and Applied Chemistry, with their own periodic table, which has now become universal. You must have seen groups like group 1A, group 2A, group 3B, and so on and so forth. If you look at this standard periodic table, you will see that group 1 that we have here is actually meant to be group 1A. Group 2A is supposed to be group 2A. And then you move to group 13, where you have your group 3A, group 4A, group 5A, 15, group 5A, 16, group 6A, group 7A, 17, and then group 7B, group 7A, group 8A for group 18. If you look at the third period, the third group here, you can now have group 3B, and it goes on like that. Why the distinction between A and B? The A's are known as representative elements. I would have asked you to define representative elements for me, but because I can't see you. But representative elements are elements that are distributed into different groups, apart from the transition elements. You can see the purple elements, including the scandium group, that is group 3 here. The scandium to the zinc group 3 to 12, down are the transition elements, because they are considered as filled D and F orbitals. Okay, thank you. I can see some of your comments. Okay, it is clear here. I can see the slide. Thank you very much. Please be very, very attentive. What I am saying here is what is going to make you understand these things. I don't want you to just read through, because I have the intention of I'm not going to give you slides. I'm going to give you a comprehensive note, and I have already arranged with some of your class reps to see me possibly before the end of today, because what I'm going to teach tomorrow, I would have sent the notes to you, and I'll highlight some things that I'll use it so as to save time and to give you a better understanding. How many of you can write correct electronic configuration? Very few of you. And I know that you think that I'm joking. Most of you write your orbitals as capital letters. In the examination, we can give you exams and ask you to write electronic configuration. You might think that we are just looking at the electronic configuration. No, there are certain things we are looking at. Orbitals are represented by what? By small letters, the lowercase letters. But most of the time, from our experience, you write them as what? Capital letters. Anybody that writes that, but you are very lucky, because what you are going to have in your exams is multiple choice. But we can still ask you such questions in multiple choice. Okay, after you have written your electronic configurations very, very well, you need to understand where electrons must be lost. If you are asked to write the ionic form of a particular element, you must know where electrons must be lost. Oftentimes, you have problems when we come to transition metals. When you have transition metals, excuse me, when you have the transition metal series, the transition metal series are those with incompletely filled D and F orbitals. Let me give you an example. Let me take iron, for instance. Iron has an atomic number of 26. Most of the time, when you want to form your ion 2 or ion 3, you miss it. For instance, let me write the electronic configuration of iron here as 26. It is 1s2, 2s2, 2p6, 3s2, 3p6. Now, you have to fill your 4s orbital first before you fill your 3d orbital, and it's going to be a 3d what? 3d6. And this is where the problem comes in. If you are going to form ion 2, most of the time, you come back to tell me that your ion 2 will now have a configuration of, because the 3d orbital was the orbital that was filled last. And they told you that your electrons must be lost from the outermost orbital. When you are talking about outermost orbital, they are talking about the orbital with the highest energy. That is the orbital with the highest energy level. How do you detect the orbital with the highest energy level? It is the orbital with the highest numeral. The orbital with the highest numeral. Each numeral denotes the principal quantum number, and it tells us the energy level of each of these. So most of the time, you would have lost 2 electrons. You would have removed 2 electrons from the 3D orbital, which is what I experience most of the time. And the configuration will now read this 4s2 3d4. No, it's not supposed to be like that. It is supposed to be 4s0 for ion 2, Fe2 plus. It's supposed to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d6. Why is the electron lost in the s orbital? Because the s orbital is the orbital of what? Of the highest energy. How did you know that? It is the orbital with the highest numeral. I can give you an that is the most stable. Stability has to do with the energy level. The higher the energy level, the lower the stability. The higher the energy level, the lower the stability. But in transition elements, because the 3D orbital is an inner element, we find it very difficult to fill such elements. So to fill such orbitals, I mean. So the outermost orbital is first of all what? Filled, before you now put all the other energy in filling the inner orbital, which is the 3D. Okay? If that is very clear to you, it is very important for you to note that writing electronic configuration of the element and the ionic state of such element is going to play a crucial role in what we are going to study today. I hope that is very clear to you so far. Okay, let me go back. I don't know how good you are. Okay, I should give you the first attendance code. Please listen to this. The first attendance code for today is 5G KNX. I should be able to type it. Okay. It is okay. 5 capital. Yes, G K N X. 5G KNX. Yes, it is there now. Ah, okay. I hope you have seen it. Or should I repeat it? Okay, that's very good. I can see some of you saying it. So please, I want you to take note of this introductory part of this. Now, I want to go back to the previous slide. I have the intention of showing the series of periodic table, but that would take some time. Now, we are talking about stability. When we say an element is stable, one element is stable than the other. What we are referring to is actually the stability of the electronic configuration. So the first thing you must understand when it comes to understanding the chemistry of any element is for you to understand for you to know how to write their electronic configuration. When you now write electronic configuration, you can now compare their stability. How do you compare this stability? From your secondary schools, you must have been told that half-filled orbitals and fully filled orbitals are non-stable. But between the fully filled orbitals and the half-filled orbital, one is supposed to be what? More stable than the other. That's why the stability of the half-filled orbitals, they are still less stable than the fully filled orbitals. Okay? Now, the unstable ones are the less than half-filled and the more than half-filled. The less than half-filled orbitals are usually the less than half-filled orbital and the more than half-filled orbitals are expected to be unstable. And what is responsible for this instability is the inequality in the number of electrons that was actually allotted to each of these orbitals. To these orbitals. Now, what do we mean by this? It's quite easy for you to understand the stability because you can identify half filled and fully filled. But when you are dealing with less than half filled and more than half filled, you have to understand the chemistry. Take note of this and let it be your guide. A less than half filled, a less than half filled orbital is usually more stable than a more than half filled orbital. A less than half filled orbital is usually more stable than a more than half filled orbital. Let me pick the d orbital here. When I'm looking at the d orbital, if you have a d3, and a d6, which of them is going to be more stable? If both d3 and d6 are unstable, because the minimum number of electrons that can make them half filled is equal to 5. But if you see the d6, it is slightly more than what? Half filled. From the statement I made, the d3 orbital is expected to be more stable than the d6, despite the fact that the two of them are unstable. You are going to encounter some configurations. Let's go to representative elements. When you have representative elements and you have a p3, they said you should compare a p3 with a p6. I'm 100% sure that with my statement, you will know that a p3 is going to be more stable. Is it going to be more stable than a p6? No, the p6 is going to be more stable than a p3 because both of them are expected to be very stable. Unfortunately, one is half filled, the other one is what? Fully filled. The maximum number of electrons the p orbital can take is 6, while the maximum number of electrons, maximum number of electrons the d orbital can take is what? 10. If you have a fully filled, that is, this is going to be paramagnetic. I hope you know what paramagnetism is all about. Paramagnetism means that all the electrons there are paired. But in a p3, all the electrons are going to be single. So this one is, no, sorry, please, I take that back. Paramagnetism is when when the orbitals are singly filled, when the suborbitals are singly filled. While diamagnetism is when the orbitals are what? Are fully filled. So a p6 is going to be diamagnetic, while a p3 is going to be paramagnetic. Please take note of that. That was a mistake, and I take it back. A p6, where we have all the suborbitals, the px, the py, and the pz orbitals fully filled. That is, the electrons are paired. That is diamagnetism. Di indicates that there are two in each of the suborbitals. Paramagnetic means that the orbitals, the electrons are parallel to each other. You understand? So it means that they are single in each of the orbitals. Now compare a p3 with a p5. Obviously, you will know that a p5, because it is more than half filled, half filled, is going to be less stable than a p3. Now, there are some parameters that you must have been taught in groups 1 and 2 of the inorganic chemistry. Please hold on. I'm coming, sir. I don't know how to erase this. Okay, thank you. Okay, now look at the third factor, trend on the periodic tables. When we are talking about trends on the periodic table, there are certain factors that we are going to take into consideration. I'm sure that the first person that taught you in organic chemistry must have taught, and groups 1 and 2 must have taught you something about electronegativity, electropositivity, ionization energy, lattice energy, and so on and so forth. And I'm also sure that you were taught in the first semester in chemistry 101, but this is 101. But this is where you are going to apply it. What are the factors? Let's take ionization energy. Each of the elements in each group are characterized by some of these factors. And as you move along or across the period, from the left-hand side to the right-hand side of the periodic table, there are variations in these properties. Let us play around with ionization energy. I would have asked you to define what ionization energy is, but you all know that ionization energy is the energy required to remove the most loosely held electron from the outermost orbital of a gaseous atom. Now, it is possible for them to ask you these questions in the exam, that you should define ionization energy. If you don't include the keywords, you might have problems. What are the keywords? The most loosely held electron, that's the first one. In the outermost orbital, that's the second one. And the third one is what? Outermost orbital of what? Of a gaseous atom. If these terminologies, these words, these adjectives are not there, you might not get the answers right. And you will think that it is a definition question and you are supposed to get it right. What are the factors affecting ionization energy? Ionization energy is mostly affected by size, because as size decreases, ionization energy increases. What are the factors responsible for this general statement? Because as the size decreases, it means that electrons are going to be lost. Size can decrease, but that is not what we are looking at on the periodic table. If you look at a particular period, probably first period, second period, third period, and you are comparing all the elements as you go along that period, you will see that as electrons are being added to the same shell, it's an indication that the effective nuclear charge would increase, because it wants to hold these electrons, additional electrons, in place. How does it hold these additional electrons in place? Because electrons are now being added, the number of electrons are increasing. Likewise, the number of protons will increase, and then the effective nuclear charge must also increase, because for the stability of an element, the electrons must be properly held in place. So as you move across the period, from the left-hand side of the same period, please take note of that. From the left-hand side to the right-hand side, electrons are being added to the same shell, and the effective nuclear charge is increasing. So in an examination, if a question is asked, why is the size decreasing across the period? You tell them that electrons have been added to the same shell, and this necessitated an increase in the effective nuclear charge, which led to what? A reduction in size. What does the effective nuclear charge do? What it does is that it pulls electrons. If the effective nuclear charge is higher, the size of the element is usually what? Smaller. So it means that the smaller the size, the higher the what? The higher the ionization energy. This is because in a very small, compare an atom of this size and an atom of this size. I hope you can see it. And they have a nucleus, the same size of nucleus. In which of these two do you think it will be very difficult to remove the electrons? Let's assume that the electrons are represented by X. I would have asked you in person, but because the size is very small, the effect of the nuclear charge is very high in the smaller atom as compared to the larger atom, because they have the same nucleus, the same size of nucleus. Therefore, to remove these electrons, it will require a higher energy. It will require a higher pull. And why is it so? Because the effective nuclear charge exhibits positivity, while the electrons exhibit what? Negativity. I hope you understand. Okay, so the larger atom would require a lower energy to remove the most loosely held electron. I hope you understand that. Now, this is the reason why as you go across the period, size is decreasing. As you go across the period, size is decreasing. And what is increasing? ionization energy. As size decreases, effective nuclear charge increases, and the energy required to remove the most loosely held electron also increases. Okay? The larger the size, the lower the ionization energy. But this is not the golden rule. The golden rule has to do with the stability of the electronic configuration. It has to do with the what? Stability of the electronic configuration. What do I mean by the stability of the electronic configuration? Now that you know how to write electronic configuration, you must know the one that is more stable than the other. I will give you an example here. Okay, it's 8:30 now. I'm actually meant to give you the second attendance code. The second attendance code here is PC JUG. I hope you have seen it. That is the second attendance code. All right. In one of your tutorials, I'm sure that in one of your tutorials, you must have been shown that where you compared the ionization energy of nitrogen and oxygen. The ionization energy of nitrogen and oxygen. Let me show you this. We all know that nitrogen is before oxygen. What is the atomic number of nitrogen? I guess it is 7. While the atomic number of oxygen is 8. When you look at this, you should be able to explain why the first ionization energy of nitrogen is going to be higher than that of oxygen. But ideally, from the definition that we gave and from the rule that was guiding ionization energy, we said as you move across the period, you will see that nitrogen, oxygen is after nitrogen, in the saying that the first ionization energy of nitrogen is still greater than that of oxygen. What is responsible for this? Nitrogen, the configuration is 1s2, 2s2, and then 2p what? 3. Isn't it? Because the atomic number is what? Is 7. Let us look at oxygen. Oxygen has what? Configuration of 1s2, 2s2, and then 2p4. I hope you are taking note of how I have been writing my own orbitals. Okay, they are suborbitals. I mean, orbitals are what in small letters, the lower case. Now, how do we compare the stability of this configuration? You can see that the 1s and 2s orbitals are fully filled, so we are not really concerned about them. Our concern here is on the 2p orbitals, where we have for nitrogen the 2p3. What does that indicate? You will see that the 2p3 indicates that the p orbital is what? Is half-filled. So it is very stable. And then for the oxygen, the 2p orbital is more than half-filled. But don't forget that when you are filling it, you have to follow Ohm's rule of what? Maximum multiplicity. While you have them being filled singly before what? Pairing would occur. You can see 3 and then 4. Remember, I told you that a more than half-filled orbital is less stable than the half-filled orbital. So you will see that nitrogen is more stable in terms of electronic configuration than oxygen, because the 2p orbital of oxygen is more than half-filled. Why is it now that it is more difficult to remove electrons from nitrogen? That is, the energy required will be higher than removing an electron. Oxygen will be willing to lose that electron. This is because you want to distort the stability of that configuration. And anything that would distort the stability of the configuration would cause problems for this. That is why nitrogen will resist it. It will require a very high energy as compared to an unstable configuration that will readily what? Give out its electron. That is the reason why the first ionization or energy of nitrogen is greater than that of what? Of oxygen. Ideally, that of oxygen is expected to be greater than that of nitrogen. But because there is a condition that supersedes all conditions, which is the fact that stability of electron configuration determines a lot of things. We are going to be looking at some of these things as time goes on. I will talk a little bit on hybridization as well, because I really understand that some of you don't really know elements that can undergo hybridization. Some of these factors I'm talking about are the ones that we are going to use in explaining the property of each element in each group. When an element belongs to a particular group, that element is said to be what? A representative element. The word representative means that it belongs to, it is a representative of a particular group. So elements in groups 1, 2, 3, 4, 5 to 18. By the time I go down, you will see that I gave you some of the various ways that you can use in identifying them. Representative elements have different characteristics. For instance, every first member of each group has an anomalous behavior. What do we mean by anomalous? It behaves differently from the other members of the group. So it is important to note all these things. Electronegativity. When you are talking of electronegativity, you are talking about size. Electronegativity, you are talking about size. All these things I will try to explain to you. I will start from our next class. Now, hybridization. Most of you just know the series of hybridization. Why do we even have to, species have to undergo hybridization? This is because we want to bring the energies of the orbitals that are involved in compound formation to the same level. So that when you have hybrid orbitals, when you have individual orbitals, and you are bringing them together, you must bring them to an equilibrium position that is permissible for each of these elements combining. That is why hybridization takes place. Before I go into that, I'm coming back to hybridization. I just remembered something now, and that is variable oxidation states. Most of you don't know that it is not only transition elements that exhibit variable oxidation states. Variable oxidation states means that the element can exist in various oxidation states. Transition elements are known to exist in various oxidation states, but this is not known for representative elements. But it is possible for representative elements to also have variable oxidation states. What condition? What is the rule guiding this? Guiding this. Excuse me. Any element and 4 electrons in its output variable oxidation states. Any orbital, any species, any atom, any element that has more than 4 electrons in its outermost shell has the ability to exhibit variable oxidation states. But their own variation is limited. It can only have 2. For instance, and this variable oxidation states can be used in forming compounds. Let me give you an example. I know you must have heard of a compound PCl3 and PCl3. 5. These are compounds that are known, that are useful in the industry, and they are considered stable. Why would phosphorus air exhibit two oxidation states? Because I know that you will see that phosphorus air is exhibiting a +3 oxidation state, while air it is exhibiting a +5 oxidation state. This is because phosphorus has more than 4 electrons in its outermost shell. There is also one problem that we encounter. Most of you don't even know how to detect the number of electrons in the outermost shell. Most of you don't know it. You are so used to the K, L, M shells. But no, right now we are using what? A complete electronic configuration, standard electronic configuration that shows the elements, that shows the orbitals. For instance, I'm still coming back to this because as I remember things that are usually causing problems for you, any element that has what? Okay, any element that has what? Can you repeat this question? Kehinde Opeyemi, can you repeat your question? Because your question is incomplete. Please do. Any element that has what, sir? Please, can you repeat that question? I'll answer it because it's incomplete. You know, I've said so many things about that, but it's very easy. I've asked your class rep for different departments to try and see me so that even if you have questions, I don't mind taking you to 1000 seater and trying to settle some of these problems, because I know that you would have questions. You will have questions, and I'm always ready to answer. So let's go back. Now, how do you use, look at phosphorus. If you use the KLM shell, you know that K, you have 2, 8, and phosphorus is what? What is the atomic number of phosphorus? 15 or 16? You will say it is 15. 2, 8 what? 2, 8, 5. You will tell me that the outermost number of electrons is equal to 5. This is not acceptable anymore. You have to write out the electronic configuration. You have to write out the electronic configuration. Let's take phosphorus here. 1s2. Okay. Any element that has 4 electrons in its outermost orbital would exhibit variable oxidation state, but there are just 2 oxidation states. But you can have some elements as we go on that will have various oxidation states, but this is because of the condition. You were saying any elements that has 4 electrons, that has more than, I said any element that has more than 4 electrons. Okay, not 4 electrons, that has more than 4 electrons in its outermost shell would exhibit variable oxidation states. And that is the example I'm giving you. Opeyemi and co. You can look at this example. Look at phosphorus. We said phosphorus is 15. 1s2, 2s2, 2p6, 3s2. This is 12, isn't it? And then what? This is 2, 2, 6. This is 10, 11, 12. And then it's going to give us what? A 3p what? A 3p3. Okay? How do you know the outermost electrons? The electrons that are in the outermost orbitals, the electrons that are susceptible to being lost. When you look at this configuration, you will see that we have 1. This is an inner orbital. You have 2, 2. These 3 belongs to the 2s and 2p belongs to the second energy level. 3s and 3p belongs to what? Belongs to the third energy level. And you will see that here The 3s and 3p are the highest orbital, and they share the same what? They have the same numeral. So all you just need to do is to add 2 to 3, which is equal to what? 5. Those are the outermost electrons. And you will see it when we were using the KLM shell that we also got 5. Okay? Let me give you another example so that you will not get confused. Let's take, let me use our sodium. Sodium is 11, 1s2, 1s2, 2s2, 2p what? 6, and then 3s1. This is very simple. All the electrons in the outermost orbital. Which orbital is the outermost orbital? That is the orbital that has the highest numeral. In phosphorus, 2 orbitals shared the highest numeral. That is the 3s and the 3p. So you add all the electrons there. But here, only one orbital has the highest numeral. So it is only one electron that will be present in what? In the outermost orbital of sodium. Phosphorus is Ishola Joy. Phosphorus is not a transition element. Phosphorus is a representative element. Okay, take note of that. Phosphorus belongs to group 5. Group 5. Oh, sorry. Okay, let me just answer this for the next code. So Ishola Joy, phosphorus is not it's a representative element. It's not a transition element. Okay. Now for the third code, please take note of the third code. The third code is 69. Okay, 69 YWT. That is the third code. 69 YWT. That is the third attendance code. Pacify Oyelami, what is your question? If you have any question, you can find time to see me in the office. But the representative elements that are distributed into different groups are passed. That is a very good one. Joshua Adekomi, that's a good one. Okay, that's a good one. But if there's any question, I'll be looking through. But we still have a lot to do. So please, I hope you got that. How to know the number of electrons in the outermost orbit. I would have given you an assignment, but this is not the time for assignment. Look at phosphorus. So let's go back to the variable oxidation state that we are talking about. Look at phosphorus. You will see that number of electrons in the outermost orbital of phosphorus is 3 plus 2, which is equal to what? 5, isn't it? So the oxidation states that will be known for phosphorus will be 5 and 8 minus 5, which is equal to 3. Did you get that? Once the number of electrons in the outermost orbital is greater than 4, the oxidation state of such an element will be the number of electrons in the outermost shell and 8 minus the number of electrons in the outermost shell. Did you get that? Phosphorus has 5 electrons in its outermost shell. So it will exhibit an oxidation state of +5 and 8 minus 5. So it will exhibit +5 plus 3. That is the reason why it could form compounds like PCl3 and PCl5. But this is not the case. This is not so in the case of sodium. Sodium has only 1 electron in its outermost shell, so it can only exhibit what? Only 1 oxidation state. Also note this, that the number of electrons in the outermost shell of an element determines the group it belongs to. The number of electrons in the outermost shell of an element determines the group it belongs to. Can we look at another example that will make things easy for you? If you have questions, you can ask me. Okay? Badamosi Yusuf, you are asking for my name. Okay. Elizabeth has already answered you. They said Professor OG, but my name is Olaoluwa Ogunkunle. Okay? I'm in chemistry, room 210. Okay? I can see somebody that has written OA Ogunkunle. That's a good one. All right. Let me pick another thing here, and that is hybridization. Hybridization does not only take place. Hybridization stabilizes compound. Hybridization stabilizes compound. I want you to take note of this rule again. I'm looking at someone, I don't really understand the outermost shell you were adding. Okay, let me explain that, but we don't have much time. Okay, let me explain that. I don't really understand. Omiwole Akorede, let me explain that again. Okay, hold on. Omiwole Akorede, please. When you write an electronic configuration, the number of electrons in the outermost shell determines the group that species will be. But I was now trying to explain to you how to determine the number of electrons in the outermost shell using the standard electronic configuration. I now chose phosphorus. You can choose another one. I chose phosphorus. Z for phosphorus is equal to what? 15. Let's now write it. 1s2, 2s2, 2p6, 3s2, and then 3p3. Now, when you look at the numerals, this is 1, this is an inner, this is 2, this is 2. Now, the number of electrons in the p orbital is equal to 8. So usually this will be your K shell, these two will be your L shell, and this will be your M shell. Why is this your M shell? Because you will see that, look at this. When you look at your M shell using the KLM, you will see that the total number of electrons in the M shell when you were calculating was equal to 5. But this is how to go about it. See, when you have the outermost shell, the number of orbitals, if two orbitals have the same numeral and they exhibit the highest number, you add the number of electrons in such orbitals. The 3s orbital is different from the 3p orbital, but they both belong to the third period. So you add the number of electrons in the p to the number of electrons in the s with the number of electrons in the b, because they belong to what? The same orbital that shares the what? The highest numeral. This gives us 5. Okay? And I gave you an example of sodium. I can give you an example of let's look at carbon. Hydrogen, helium, lithium, beryllium, boron, carbon. Carbon is 6. 1s2, 2s2, 2p what? 2p2. The total number of electrons in the outermost orbital of carbon is equal to 4, because these are the highest numbers. These orbitals, the 2s and the 2p, carries the highest numeral. And because they are carrying the highest numeral, the number of electrons in both orbitals are to be added together, and that will give you the number of electrons in the outermost shell. This is the reason why carbon will form 4 bonds. Okay, sir, if the outermost shell is more than 4, how can we calculate the outermost shell? Okay, if the number of electrons is greater than 4, don't forget the oxidation state is going to be equal to that number of electrons in the outermost shell and 8 minus that number in the outermost shell. Do you understand that? Okay, now I want to okay, all right, let me round up with hybridization. I don't know what you must have been taught in hybridization, but this is a gospel truth. orbitals, electrons that are not within a particular period cannot undergo hybridization. There are some periods that are designated for hybridization. What happens in hybridization? There is an expansion. There's a promotion of electrons from one orbital to a higher orbital. As a golden rule, no element outside the third period, or let me put it this way, only elements in the third period and downwards can exhibit hybridization. Awotubo Alexander, you are asking whether I dropped the third code. I did. Okay. Only electrons that are within the third period and downwards would exhibit hybridization. This is because the 3D orbital starts in the third energy level, and usually electrons are promoted into the D orbital. They might not tell you this. Some of you might be talking about carbon. Some of you will be talking about carbon, that carbon exhibits sp, sp2, sp3 hybridization. No, that is what? An interrelationship, an adjustment with orbitals. But this time around, when you receive the real hybridization, it involves the d orbitals. And because the d orbitals, the first set of d orbitals is in the third energy level, no element outside the third energy level would undergo hybridization. The period 1 and period 2 elements cannot undergo hybridization, but periods 3, 4, 5, and so on and so on, and so on and so forth, would undergo hybridization because they have vacant d orbitals, vacant d and f orbitals into which they can promote their electrons. And this is going to lead to what? Complex formation. There is no time to actually explain this, but there's no time to actually explain this very well, but probably I will take some time to explain it in the next class. I will soon be rounding up. I think I have about 2 more minutes, I guess. Okay, look at what I said. I want you to have a look at the group elements, group 3 elements. These are the members of the group 3 elements, their symbols, their electronic configuration, and look at their oxidation states. Look at their oxidation states. I would explain those ones to you tomorrow. Coordination number. When you are talking about coordination number, it is an indication of the number of bonds those elements can form. You can also look at group 4 elements, because I'm going to deal with group 3, group 4, and then group 5 elements for you. Look at the elements, look at the configuration, what they stand for. You would actually see them. I will start from this place tomorrow. And if you have any questions, like I said, I'm very easy to find. Okay, just come to White House and look for that man that wears shorts. Okay, and I'm very, very unique about that. And like I said, your class reps are going to come around, and I don't mind for as many that would love to come after my classes or in between. I can have a physical class with you in 1000 seater so that you can have a better understanding. Because take note of this, you don't cram my own course. You have to understand it, because what I will ask you are technical questions. Do have a wonderful day, and it's so nice talking to you all. God bless you all. She's Uncle, bye.
Good morning, class. Good morning, class. This is your friend Ezekiel once again. Want to apologize for what actually happened last week, Friday. If you are there, let me just see yes, 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 yes. Last week, Friday, I was trying to complete magnetic field with you. Oh, thank you. Good morning. To complete the magnetic field with you guys, unfortunately, there was power failure. And I waited till the end of the till 10 o'clock, the light was not restored. So this morning I will start from where I stopped on Friday. If you can still remember, I started with magnetic force on the current carrying wire. Okay, so and I tried to explain that assume that we have a wire that's actually fastened fixed on both ends, and it's actually passing through the hollow of the magnetic field, and assuming there is no current actually passing through that particular wire, there is not going to be any deflection. So assuming that we allow current to actually pass through the magnetic through the wire, we can see the direction of the current up like this one, and there's going to be deflection of the wire towards the right. And if the direction of the current is downward, they are going to see the deflection towards the left hand side. And I try to remind you on that day that you remember the equation of motion that stated that the distance is equal to the time multiplied by the speed, which is this particular equation. And I also said that if you can still remember the charge, which is equal to the current times t, which if you now substitute the what we have for the t here, you will have this particular equation, yes or no. So and where I stopped on that day is that I actually made mention that the relationship between the magnetic field and magnetic force is equal to the current multiplied by the length of the wire and that of B, which is the magnetic field. Assuming the magnetic force is assuming that the magnetic field is perpendicular to that of the force and that of the velocity. Okay, so on that day also I say assuming that it's not perpendicular, we are going to have the angle which is going to be angle phi. Okay, so and I say in this case we are going to have the length as a length vector. Okay, so where I actually stopped on that day is where I was trying to solve this simple equation. I said assuming that we have a straight horizontal length of copper wire that has a current I equal to 28 equal to 28 ampere flowing through it. I said, what are the magnitude and the direction of the magnetic field? B, needed to suspend the wire, that is, to balance the wire gravitational force. Okay, if you can see, no, this is physics PHY 102, not CHM. Thank you. Joshua Adekami, this is not chemistry, this is physics, okay? So, and as I said, if you want to actually solve this simple problem, you are to determine the magnetic field. If you can see from what you have here, you are giving the current to be 28 ampere, and you are actually giving you are giving the mass per unit length, that is the mass all over length equal to 46.6. So we can now say the mass is equal to 46.6 multiplied by L, multiplied by the length. Okay, so from there we can still remember that our simple formula that stated that FB equal to I L P sine theta. Okay, so and since we know that it is perpendicular, and you can see there is a force of gravity that actually acting on that particular wire, we can equate the F equal to mg. So we can now say that since it's perpendicular, we know that sine theta is going to be sine 90, which is equal to 1. We can now say I L B equal to mg. But remember, from this side, I said mass is equal to the 46.6 times L. So we can now replace the L here by this value. We now have I L B equal to 46.6 L multiplied by G. Okay, so from there we can divide the both sides by L. L can actually cancel out. So from there, we are to determine the B. So B is equal to 46.6 G all over I. So where our I is equal to 28. So if you substitute A to 46.6 times 9.8 all over 28, you are going to get 1.6 times 10 to the power minus 2 Tesla. Okay, Ezekiel, calm down, P trial. Thank you very much, but I don't think I'm not too fast this morning. So what I just saw for you here is what you have here on the screen here. So if you do it correctly, you're going to get this answer. Is that clear? So let me just dictate the first code for you. Listen to the first code. I will also type it as well. Z N S 4R. Z N S 4R. So that is the first code. Plug in the first code and we will continue. Okay. The first code is Z for Zion, N for Neon, S for Stephen, 4, and R for Rutherford. Okay. Thank you. So if we now continue with, I want to actually try to explain something to you on torque. Many of you have actually come across this torque. Much of the work done in the whole world is by electric motors. So the force behind this work are the magnetic forces that we are currently studying now. So as you can see, there is an electric motor in form of a rectangular form placed at the center of the magnetic center of magnet. So, and if you can look at it, you can see that it is consisting of a single current carrying loop immersed in a magnetic field. So the two magnetic force produce a torque on the loop. If you look at this particular one, you can see F4 and F2. The F4 and F2, they have the same magnitude and they act opposite direction to one another, to each other, and they will actually cancel out. So that is, since F4 and F2, they are opposite, they have the same magnitude, they will cancel out and they will become 0. So now the only force that we act on this particular motor is going to be F1 and F3. Assuming we place the F1, F3 in form of this particular one, we can see that there is a normal factor N act at angle theta. So we can see what is going to happen here, that we need to find the net force and the torque acting on the loop in the orientation. excitation. Okay, so from there, how are we going to actually do this? If you look at the next slide here, what you can see here is that F2 is equal to I. I is the current passing, and P is actually the length here, okay, and that of B is the magnetic field, and which is, since it's acting at angle theta, which is sine 90 degree minus theta. So this one is actually F2 is going to be equal and opposite to that of F4. So, and since they are going to cancel out, they are going to become 0. Okay, so we are now left with that of F1 and that of F3. So as you can see, the F1 and F3, look at this F1, F3. Oh, I hope I'm not too fast. Oh, thank you. Oh, want to fall, it cannot be talking slowly. Oh, so I'm sorry. Am I talking too fast? I don't think so. Okay. Adeyemo, rain want to fall. It can talk slowly. Okay, but rain is not falling here. Okay, I will talk slowly. Thank you. You are too fast. Okay, all right. I'm sorry then. So what I'm trying to say here is that we have a talk on the current loop. And I said that particular loop is inside it's a rectangular loop inside a magnetic, inside a magnet in form of a motor. So, and I said the force acting on that loop, F4, F2, F1, F3. And I say F4 is equal to F2, but in opposite direction. I said they can cancel out and become 0. And I said we can actually determine the F1 and F3 because we want to determine the net force. So net force, which is going to give us the net torque. Okay. So as I was saying, I said here, I said the F2 equal to IB sine theta, which is going to be equal to F negative of F4, which is going to actually cancel out. And I said that of F1, the total torque, which is the torque, is this, which is equal to the distance, which is distance multiplied by the net force. Okay, so and that particular distance is what we are going to we know that distance. We want to determine the net force, which is going to be net force is equal to the that of theta 3, theta 1 plus that of theta 3. Okay, so from there, if you look at what we have here, and if we multiply this one by that of the distance, it's good. And mind you, F itself is equal to the ILB. Let me just clear it so that it will not actually mess up the everything on something. Okay. So what we are saying here is that if you look at where we can, someone want to ask us, how do we determine B over 2 sine theta? B over 2 sine theta is actually the torque moment arm, which is actually equal to the distance. This one is actually equal to the distance. If you look at here, this is how we got that one, the distance sine theta, or half of this B. That's how we got that particular, this one. So from there, we can now have the torque for the F1 to be this one, and the torque for the for the T3 is this one. So if we add the two together, we are going to get I, A, B, capital B sine theta, where A and B is equal to the area of the loop. Okay, are you following? So we can say when a current carrying loop is placed in a magnetic field, the loop tends to rotate such that its normal becomes aligned with the magnetic field. Okay, so but one thing you need to understand here is that we are trying to explain the torque on a current loop. Let's now assume that that loop is actually made up of a current coil, as if the coil is only one, because the number of coil actually determine the strength, the force, and the torque that will actually exert on that particular motor. So we can now say, assuming we have a coil contain N loop, that N can be 1, can be 2, can be 3, can be 4, depends on the number of the loop and each of them has area A. So we can now say the force on each side is n times the larger. That is, we just use the number of turns to multiply the torque. So from there, we can now say we have Ni AB, capital B, sine theta, where the one in bracket, Nia is what we actually know as magnetic dipole, and we read it as mu. So it's magnetic dipole. So we cannot say where N is the number of turns in the coil, A is the area of each turn, and we can say I is the current, B is the field magnitude, and theta is the angle between the magnetic field and the normal vector. Are you following? Okay, thank you. So now, if you can look at what we have here, I say, assuming we have a current coil with certain number of coil, maybe one coil, two coils, three coils. So we can now say the loop there may be n. So it can be any number. Okay. So here, say something from the last side where we have the top equal to this Nia sine theta. So and we have what we have here is actually the magnetic dipole moment of the coil. So to account for the torque on the coil due to the magnetic field, a magnetic dipole moment is assigned. So from there, we can have if we want to incorporate the magnetic dipole moment to it, we have what we call this particular one. Is that okay? So I believe you can still remember that you are actually taught this one under the electric field, where you have the torque exerted by electric field to be P, which is a electric dipole moment multiplied by the electric field. Okay, so if an applied torque rotates a magnetic dipole from an initial orientation theta 1 to another orientation theta f, we can say the work done on the dipole by the applied torque is actually equal to the work done final minus that of work done initial. Okay, just to understand what I've actually explained to you better, you know my mode of teaching. I like to actually quantify what I'm teaching you by actually giving you one simple calculation which we can actually solve together to actually make us to understand it better. Is that okay? Okay, so now we are giving this simple question. A circular wire loop. If I should ask you, when we say a circular wire loop, how many number of turns is that one? A circular wire loop. What will be our N? So, and I know majority of my students will get that the number of N there is 1. Yes or no? That is a circular wire loop. Okay, and we are giving the radius to be that of, thank you very much, Mayowa, and the radius is 15 centimeter, carry current 2.6 ampere. So it is placed so that the normal to its plane make an angle of 41 degree with a uniform magnetic of magnitude 12.0 Tesla. You are to calculate the magnitude of magnetic dipole. How many of you still remember the formula for magnetic dipole? Mu is equal to N I what? That of area. Yes or no? And they say it carries a current of the radius is 15 centimeters. So that is in a circular form. Area. And what will be the area? The area will give us as what? Pi r what? Pi r square. That is, we can now say N I dot pi r square. But mind you, remember to convert this one to meter. Yes or no? So do it correctly, you should be able to arrive at this simple, you should be able to arrive at this 0.18 dot meter square dipole moment. So to actually to understand which is the number of loop to be one, the dipole moment is a meter square, an ampere meter square. Is that clear? So from there, we are now to determine the torque acting on that particular loop. Since you have already determined the magnetic dipole moment, to determine the torque is going to actually be this one, B sine theta. And we know we have determined this one, and we know this one to be 12, and we know this one to be sine 41. Easily, you should be able to get the answer to be 1.45 Newton meter. Is that clear? So what I just explained here is what you have on the screen here. Is that clear? So mu, which is the magnetic dipole moment, equal to NIA, and pi r square, convert this one to meter, and you get this one. And from there also you plug it in and you get this one. Is that clear? Okay. So let me give you the second code now before we continue. The second attendance code is H8DJL. That is constant. A is a constant. So the only thing that is not constant there is that communicating. Though I'm not supposed to do it for you guys because it's supposed to be homework, but just to give you hints. This one, that's why I'm actually doing it. So what this one is all about here is this. Okay, how many of you are following the first example? I'm trying to actually first homework. I'm actually going to give you the hint. I said the first thing you need to know here is this. You quickly remember that QVB is equal to the centripetal force, which is mv square all over r. Make this one, make V as a subject of formula. We have what we know as a V equal to M equal to Q B all over what? QVR all over M, right? So if you have this one, now write the kinetic energy, which is equal to the KE equal to half mv square. So if you substitute the V here, what you are going to have, and we say this, you know that Q is a value, B is a given, which is constant, and the mass is given. So all what we don't have here is R. So we can say K E equal to 1 all over 2 Q B R all over M all square. So from there, this one is a constant. So what you are going to have, we're going to have KE directly proportional to the square of the R. So if you get this one, that is just going to be the correct answer for you. So the second one, you are to determine what? You are to determine a loop of wire carrying a current of 2 ampere is in the shape of a right angle triangle. So if you do this one correctly, what I expect you to actually get for this one supposed to be, though I won't solve it for you, that's why I call it homework. I just want you to actually lay your hand on it. If you do this one correctly, the answer is supposed to be 0. So, and if you do the last one correctly, so if you are unable to get it, ask your friend to actually solve it for you and try to understand it on your own. So if you do this one correctly, the last one supposed to be 0.251 ampere meter square in the direction of positive of K. Direction of positive of, that is in Z direction. So if you do this one correctly, you should be able to get this one. And the third one, if you do it correctly, you won't get 0 for the third one, because the third one is perpendicular, not parallel. Because this one is parallel, that's why we got 0. If this one is not parallel, you are going to get a value for this particular one. Is that okay? So this one's supposed to get, you're supposed to get 0.3 Newton for this one. Okay. So if you now go a bit further, this is just a summary of magnetic dipole as I've already explained to you. Oh, your result. I've actually apologized on Friday. Maybe because you are not here on Friday, that is why you did not actually get the information. I said we have done it on our own part. We have uploaded the result. My HOD has already approved the result, but we don't know what happened to the server, and we have communicated. We have communicated them in Inteku, and they are working on it. Some of you actually came to my office on Saturday, and I tried to actually correct you that you don't come to lecturer's office on Saturday. When he's around on Saturday, he's around for his own personal assignment, not to attend to students. Okay? And as I've told you, you people actually did well, but I want to actually do much more better in second semester in Physics 102. So, and if I say, as will be entertain all of you to come to my office and I will be showing you your result, this is what you get, this is what you get, and I have friends, all of you are my friends, I have 5,000 students. You know, I cannot entertain all of you, and if I allow only one person to see it, I need to allow start with only one person. All of you must actually see it. Just please, just be patient with us. Before this week runs out, you should be able to see your result. Thank you. So, and I think I asked my colleague to actually send this particular slide to you. Okay. So now we want to actually jump to the second part of my own part, which is magnetic field due to current. We have studied magnetic field, and now we want to discuss magnetic field due to current. Here, the first question you should ask yourself, I always ask myself, what is the physics behind magnetic field due to current? And also, you will ask yourself, how can we calculate the magnetic field due to a current? And after we have actually determined that one, how are we going to determine the force between two parallel currents? You cannot see. You cannot see what? You can't see the slide? Hello? Can you see the slide? You only see my face. You can't see the slide. Is that so? Okay, just hold on for me. Okay, just a minute. Just a minute. Can you see it now? Oh, you are seeing it now. Oh no, the homework, I've done that. I've sent you have seen that one already. Can you see the slide? So we should continue. No, I can't show the assignment again. If you have already shared the slide with you guys, okay, and my colleagues as well, okay, you can see the slide now. Let's continue. Thank you very much. So this part is magnetic field due to current. So I said the first thing I need to ask myself here is that what is the physics behind this magnetic field due to current? And after that, we calculate the magnetic field due to a current. And not only that, we are going to determine the force between two parallel currents. We will actually explain Ampere's law. We will explain the solenoid and toroid. And we also explain a current carry coil as a magnetic dipole. If you cannot see the assignment or the homework, ask your class rep to actually share that one with you, because I believe my colleagues has already shared the first slide, the magnetic field, with you guys. You should be able to see the homework there. And if he has not shared the slide with you, as soon as I'm done with your class, I will communicate him to share it with your class rep. Is that okay? Let's continue with the magnetic field due to current. So under this particular aspect, the front one thing that will come to your memory that you need to understand here first is this. Basic observation in physics is when a charged particle move. That is, when a charged particle move, we said it produces magnetic field around itself. You agree with me? So, and our first step in this aspect is to find the magnetic field due to the current in very small section. Let's assume that we have a very long wire of arbitrary length, and the length is not actually regular. The best way to actually determine the force acting on that particular wire carry current is to take a small portion of that wire and determine the force acting on that particular small portion. Okay, so but before we get to that one, if you can see here, as a moving charge particle produces a magnetic field around itself. So thus, a current of moving charge particle produce a magnetic field around the current. So the feature actually made use of electric and magnetic effect. And as I've told you from last week Monday, I said magnetic field is applicable to all field. So you can see this particular guy actually placed a device on his through his ear. That this device is what we call magnetoencephalography. It's a device that's used to actually determine the activities of brain when a student is actually reading. So when you are actually studying, your brain is actually producing magnetic field, okay? And to detect that particular magnetic field, there is a special devices needed. So for those of you that you are in earth sciences, you may likely come across something like this, and the name is magnetoencephalography. That we call it, short is MEG. The short form is MEG, okay? So that this particular one is what normally used to actually determine the electric field when students are actually reading, okay? So from here, if we now go a bit further, I said magnetic field due to a current. The magnitude of the field, dB, produced at a point P. So I said when we have a wire of arbitrary length, the length is not regular, we just take a portion of that particular length. As you can see, we call that the length of that portion to be ds, okay? To be ds, okay? So from there, we can determine the magnetic field acting at this particular person with angle theta. So we cannot say this the current actually the current length is IDS. That is the current length of this particular small person is what we know. I think the current length is what we know as IDS. From there, we can say the dB, that is a differential of magnetic field, is equal to the mu, which is permeability, all over 4 pi multiplied by the current length, which is what we know as IDS sine theta, all over the square of that particular distance r here. So from there, to compute the magnetic field from any electric current, we have to choose a differential element of a wire of length ds. So we now get what we know as a current length in form of this one. So there is a guy, two of them actually combined together. They actually solve this simple problem where we know their name is Biot-Savart law in the vector form. So from there we can now say the mu, which is permeability, all over 4 pi multiplied by IDS, which is the current length, cross product of that r all over r square. Okay, so from there we can actually, that is when we have of arbitrary length, assuming we have a wire that is very, very long, an infinite long straight wire carry a current. To determine the magnetic field generated at a point, let's that this point there is that are located at a perpendicular distance r from the wire. We have to choose an element ds. So from the word about Savart law, he said the B point into the page. This is the vector form of the Biot-Savart law. So if we try to integrate this particular one, we can say this law can be used to calculate the net magnetic field produced at by various distribution of current. I hope I'm not too fast, or am I too slow today? I know my students will say, Ezekiel, you are too fast. Is that what you are going to say? Okay, Ezekiel, calm down. Not Baba, calm down. I'm not Baba. I'm Ezekiel. Okay? So just try to understand what I'm trying to pass across to you. I said, assuming we could not see the homework. If you cannot see the homework's time has already passed, I will share the slide that contain the homework with you as soon as I leave the class. Is that okay? So what I'm trying to say here is that let's just concentrate on magnetic field carry current now, due to a current now. And when we are done with this one, we will attend to that one later, okay? So as I've explained to you, I said I want to determine the magnetic field of a current, of a wire carry current of an arbitrary length. I said you just take a portion where we have current length IDS, okay, and I said the B more equal to permeability all over 4 pi times IDS sine theta all over r square. That is for this particular person. So, and I said where theta is the angle between the direction of the ds and r. So, in order to compute for wire that we don't even know the end, I want to determine the magnetic field acting at this particular point. If you can still remember when we started the magnetic field, I said something on that day. I said, assuming you have a bar magnet and you have a magnetic material like a iron or nail, and you place it very close to that magnet, when you get to a certain region, you are going to actually experience the force drawing that magnetic material towards itself. Is that clear? So the same thing applicable to wire. We have a very long wire. We don't even know the end of that particular wire, and you pass current through that particular wire, and you have a magnetic material very close, maybe at point P. So what you are going to experience is that you are going to experience magnetic field at this particular point to determine the magnetic field you are experiencing at this particular point is what we are trying to determine here. So in that case, we have a particular formula for that. So, and I said, in case you don't know the length of that particular wire, we can actually arrive at this particular formula, which is B equal to mu naught I all over 2 pi r, where the r is this particular one. Okay, so that is for long straight wire. Assuming we have semi-infinite straight wire, semi means 2. What you have here, just divide by 2, you will have the semi-infinite straight wire. Is that okay? All right. So for this particular one, we can also apply it to a circular magnetic field due to a current in a long straight wire. We can actually apply this simple formula to magnetic field outside a long straight wire with current. So assuming we have a straight line wire in this particular form, which is actually circular, we are going to actually derive the magnetic field to be mu, which is permeability, multiplied by the current all over 2 pi r, where the r is this particular one. Okay, and for a straight wire with radius r, which is capital R, and small r here, we can apply this particular one to it because it's inside the straight wire. We are going to take into consideration just the radius from here to here and this one to here. So from there, we can actually just plug in what we have here, and we have r squared mu naught I all over 2 pi r squared. For when I ask you to determine the magnetic field inside straight wire, this is the relevant, this is the correct formula to use for that one. If it is outside the straight wire, this is the formula to use for that one. But as you know me, before I actually finish today's class, I'm going to actually show you maybe 2 or 3 or 4 work example to actually see how you should expect question in relating to this particular in relating to magnetic field due to a current in a long straight wire. Are you still following? Yes. Okay. So, and you still remember from the previous class under the magnetic field, I explained something on right hand rule. Okay. So to know or to determine that when you have a coil or a current in a circular loop, how are you going to determine the direction of magnetic field or the direction of the force there? So you still remember, grab the element in your right hand with your extended thumb, pointing in the direction of the current. The current is actually pointing downward, and the direction of the magnetic field is actually going towards this side. And if it is going up, because your hand, if it is going up, the current is here, and that of direction of magnetic field is going towards this side. So that your fingers will then naturally coil around in the direction of the magnetic field line due to the current element. Okay, so and yes, you will be thinking maybe I'm not too fast, but I don't I don't want to derive the formula for you. But the best way to know how to apply the formula is when you actually solve as many as possible questions. So, and as I've told you, I don't expect you to memorize the question in your slide, because you are doing CBT. The question that you may yes, it's going to be of the same weight. Don't memorize the answer, but try to understand the logic, okay, the method, so that if they ask you question with maybe in similar to what I've actually taught you in class, so how to actually, you need to understand it better, and for you to actually know the right formula to apply, you need to practice more. But some of you are not doing many courses, so I believe you should have enough time to devote for physics, for CHM, for MTH, and for all your courses. And as I used to pray for you, I wish you all the best. Okay, so now let's continue. Let's assume that we have a circular arc of wire. So circular arc of wire, as you can see it here, we want to determine the magnetic field due to a current in this type of wire. So just like as we have done from the previous slide, we have dB equal to mu naught IDS, which is the current length sine 90 degree all over 4 pi r square. So if we actually integrate this one, we are going to have what we are going to arrive at this particular one. So which is what we call the magnitude of the magnetic field at the center of a circular arc of radius r and central angle phi. And remind you, this angle is always in phi. Okay, it's always in radian rather, carry current. So the applicable formula to use to determine the magnetic field due to current in a wire, in a circular arc wire, is this particular one. That is, we have the mu naught permeability multiplied by the current, multiplied by the radius, multiplied by the central angle, which is phi, all over 4 pi r. Okay. So from there, also, if it is a circular, as we want to apply it to a current carrying coil as a magnetic dipole, you still remember the magnetic dipole. From there, we want to look for a way to incorporate the magnetic dipole there. So at the center, we have this particular formula, but we have a particular formula, which is, but at the center of circular arc, we have this one. But for the full one, we have this particular one. But I don't want you to confuse yourself. The best way to master this one is by using simple example. Let's now try to solve this simple example now and see if you actually understand it or not. Oyibo, why do you say, oh, they no send rubbish? Don't use foul language, okay? It's not good. Okay? Thank you. Don't use foul language again. Please, who have the previous slide? I will make sure the previous slide is sent to you immediately after the class. Though I told my colleagues to send the slide to you. Oh, who has he will send it to you, he will drop it for you, no problem. Just wait. Just concentrate on this one now, okay? So, as I've said earlier, we want to use this simple example to see if you are actually following what I'm teaching you. I said a surveyor is using a magnetic compass, and that the length of that compass is what? The radius of that compass is 6.1 meter below a power line in which there is a steady current of 100 ampere. You are to determine the magnetic field at the site of the compass due to the power line. If you can see, I don't know how many of you have passed through under the power line of high tension before. And I remember when I was still in the village, there's a high tension power line actually passing through close to our own house. Whenever we actually we spread our clothes outside, when you are passing through there, if you touch the wet cloth, you actually experience a magnetic field in form of electric shock. So that is what we are trying to actually say here. So they have a magnetic compass of 6.1 meter below that power line, which there is a steady current. The current passing through that power line is 100 ampere. You are to determine the magnetic field, which is B. But mind you, magnetic field is mu naught I all over 2 pi r. You can see the compass is a circular, right? So, and the radius is 6.1 meter. So from there, to get this one correctly, you remember the mu naught, which is permeability, is a constant. It will be given in the exam, is actually 4 pi times 10 to the power minus 7. Okay, that is the permeability. But don't memorize it, it will be supplied to you. And we said the current is 100 ampere. That is 4 pi times 10 to the power minus 7 multiply by 100 all over 2 pi, and you are giving this to be the radius times 6.1. So if you do it correctly, you should be able to arrive at 3.3 3.3 times 10 to the power minus 6 Tesla. So how many of you are following? Oh, I can see you are. Is this way? You swore say you be student. Adeyemo, don't mind him. Just follow what I'm teaching you. Okay. So the first one, you determine the magnetic field to be this one. And they now ask you from the B part, will this field interfere seriously with the compass reading? Since the horizontal component of the earth is 10 micro Tesla. That is, if you can convert this one to micro, it's going to give us 3.3 micro Tesla. Divide this one by that one, which is over 20. This one, you will have 1 over 6. That's so that it's going to interfere with the compass. Am I communicating? Let me give you the last slide, and the last code rather. The last code, are you there for the last code? Is 9 R X D 6. I've already typed it for you. I want to do it again. 9, figure 9, R for radius, X for X-ray, D for goat, and figure 6. Is that clear? That is the last attendance code. Okay, so what I explained to you from the first slide is what you can actually see here. We have this guy. This is the constant. It will be provided for you, and we have the magnetic field, we have the current, and we have the radius of the compass to be 6.1. We get this one, and this is about 1/6 the magnitude of the earth field. Therefore, it will affect the compass reading. Okay, so I always like to give you classwork, and that classwork is not only to just keep it in your phone, or it's for you to actually attempt it. If you look at the first question here in the figure, the current element IDL, the point P is here, and the center vector 1, 2, 3 are all in the plane of the page. The direction of dB due to this current element at the point P is what? So if to get this particular one correctly, so you can see, you can just try to remind yourself of the when you plug in the formula, you are not to calculate anything here. You just want you to know if you understand this particular, they want you to know which direction is magnetic field is going to actually point towards. But you can argue it's going to point into the page. Okay. So if you look at the second one, you are to determine in this figure if the current element has a length of 1.0 mm. Mind you, you have to convert it to the nearest meter. Carries a current of 2.5 and is a distance of 4.8 centimeter. Mind you, convert it to meter from the point P. What is the magnitude of the magnetic field at point P? To solve this one correctly, you remember dB equal to mu naught dot IDS sine theta all over 4 pi r square. So if you do this one correctly, you should be able to get the answer to be 5.4 times 10 raised to the power minus 8 Tesla for this one. Okay, so if you do this one correctly, that's what you're supposed to get. And for the last one, the question 3, just plug in B equal to mu naught I all over 2 pi r. So this one you're supposed to get 2.0 ampere. Is that clear? So the answer, let me dictate the answer for you again. The answer for the first one is going to, the direction of the magnetic field is going to be into the plane. The second one, if you get correct, you're supposed to get 5.4 times 10 to the power minus 8 Tesla. And the last one, you're supposed to get 2.0 ampere. Thank you, thank you, thank you. We will not be able to meet on Wednesday. I will meet you on Friday, okay? So, and I believe you are actually preparing for your test. So we meet on Friday. I won't come on Wednesday. We meet on Friday. But mind you, my part, magnetic field, all what I'm teaching you, it will not actually appear in the test. Okay? The test will contain the first two lecturers. I hope and I believe before the end of this week, you should be able to see your result. And I want to guy that actually score 98%. That 98, I know someone scored 98% in Phys 101. Thank you having me. This is where we are going to stop today. Thank you and God bless you. Thank you very much. Yes,
Okay. Thank you, sir. Yeah. Good morning, class. I hope you had a splendid weekend. We will continue from where we stopped on Friday with our lesson, our course, which is Physics 104. We started with sound waves, as you will recollect, and I will try to explain what sound wave is. That's a longitudinal wave. But don't let me drag issues here, because we did that the last time, and just conclude with what we were unable to do. And that we were unable to do is we're trying to look at an example. Then there was break-in transmission. And that question is, what is the speed of sound in air on a summer day when the temperature is 35 degrees centigrade? I was trying to let us see how to solve this problem, even though it is very direct, very straightforward. Let me also say that this is a three-part question that speaks to the speed of sound in different media, which we shall see very soon. So you see that what we're given the temperature to be just hold on for a moment for me. Just hold on for a moment. So, yes, I'm okay now. So you can hear me. So, I told us that this formula, the very first formula I gave us the other time, is works with absolute temperature. And absolute temperature is such that when you are given temperature in degrees centigrade, you convert to Kelvin. That's the absoluteness in the temperature. So that's why the 35 degrees centigrade or degrees Celsius that we're given is converted by addition of 273, as we find here, to get 308 Kelvin. And the speed of sound, if you look at the equation, is only 331 multiplied by that temperature that you are given, and over, that's the ratio of 273. So when you substitute all the values you are given, and the only value you are given that is this 308. So you will get, and if you do it well, you get about 351.5 meters per second, which was rounded up to 352 meters per second. Let's look at the question again. The speed of sound in air. Forget the summer day. So it gives 352. Let me say that we should recollect the table I showed us the other time. It will become apparent in a moment. So the other leg of the question is, if a solid bar of aluminum 1 meter long is struck at one end with a hammer. Recollect the table. This is an aluminum bar, solid. A longitudinal pulse propagates down the bar. And when that happens, you are asked to find the speed of sound in the bar. Please pardon me here. I just realized this morning the Young modulus of Y is 7 times 10 to power 10 Pascal. That's what is there. Pardon me, please. And the density, which is rho, is 2.7 by 10 to power 3 kilogram per meter cubed. And you recollect that our expression is that of the speed of sound in a solid. That's our expression. Already you are given the Young modulus Y to be this, and you are given the density to be that. I've corrected it. When you substitute, without wasting our time, when you substitute and you do properly, you are a sophomore. You should know. This one should just be pieces of cake for you. The answer you will get with that speed of sound in that aluminum bar would then be 5.09 times 10 to the power 3. 5.09 times 10 to the power 3, 5009.0123. That's about 5,000 meters per second. 5,000 meters per second. Roughly, it can be expressed as that. Let's go back a little bit. 352, 5,000 meters per second, 352 meters per second. Also take note of that. In air, as a medium, you have hundreds of meters per second. In a solid, you have a few thousand of meters per second. 1,000, hundreds, one is bigger. Let's go to this third part of the equation. The third part of the example, pardon me. You are then asked to calculate the speed in ethyl alcohol. Don't forget that table. We also have fluid. Fluid in ethyl alcohol. So that in fluid, the bulk modulus, the density is 806 kilogram per meter cubed. And the bulk modulus B is this. Please correct that. 806, this is 806 kilogram per meter cubed. Per meter cubed. And, pardon me. So this is 806 kilogram per meter cubed. And this is 1 times 10 to the power 9 Pascal, as you have seen here. So what you find is that when you substitute, that's the second formula. When you substitute, you get 1.11, 111, let's say 0 here. This is 0. And when you say 1, 2, 3, so you get about 1,000. Roughly, we can say that 1,000 meters per second. What do you think is obvious here? In the fluid, in here, in solid. We have done the example of, we started with gas, that is in here, followed by solid. So we have 352, we have 5,000, we have 1,000. What it speaks to us is that when we compare our result, we'll see that the speed in solid is the greatest, is the highest, which was a confirmation of our theory on the table that we have before. The speed in fluid, which is ethyl alcohol, now liquid, is 1,110 meters per second, while that of gas is 352. What you should take note is that sound travels faster in solid. It travels faster in solid because of tightly connected molecules. Little bit slower in liquids than that of solid, and slowest in gases. So that is by way conclusion of our class that we had last time before our stroke. Today, we are to consider intensity, Doppler effect, and interference of sound waves. That's what we are to consider today. And to do that, I will want to call our attention to Have we ever been to parties where we sit very close to speakers in the party? Do we recollect how we feel when we then sit distance away from the speaker, bellowing sound or music? How do we feel? I want us to put that into proper perspective. So let me quickly say that we have divided so far. We have been able to categorize frequencies into three: audible, infrasonic, and ultrasonic. We also learned about the application of ultrasonic imaging, not infrasonic. Ultrasonic sound in getting image of fetus, for example, using piezoelectric effect. And by the example I just showed to us, we have been able to see how we can calculate speed using different formula for different media. Now, today, it's important we know that how much energy our sound carries. And that was what I was talking to Ross about. Just that when we go to parties and music is being played at loud intensity or loud decibel, and we sit close to the speaker, how do we feel when we speak away? Sometimes I actually wonder, at clubs, why do people like to blast music at high volume when you don't have to speak to each other, you don't have to speak to your ears, or even shout on top of your voice so that the other person can hear you? Why not just lower the volume and then enjoy conversation? What is in the noise that you put or you risk your ears into going deaf? So it's because sound waves carry energy. And when they do so, when you look at the formula for energy, now we go straight into the work. Energy, the intensity, is the volume that we'll put up. Some people in their cars, they will do that blasting music. In clubs, blasting music at high volume. When you do that, what you are invariably doing is to raise the intensity, and intensity is defined as the power per unit area. Of course, power is energy over time. So that's why you have the expression here, which is then power per unit area. And it's simply the rate at which energy flows through a surface perpendicular to the direction of the wave propagation. Power or intensity, or maybe I should say that our ears, the hearing through our ears is not linear. It's not linear in the sense that you say you hear a sound 10 times more intense doesn't sound 10 times louder to our ears. 10 times more intense will sound about twice as loud, because another way of looking at intensity level, let me quickly go to that, is a logarithmic scale. I'll come back into it in a moment. So let's come back to this. Our hearing, we said what we can hear audible. Recollect, we said is 20 to 20,000 hertz, which I will write kilohertz. That is the region in which the ear can accommodate. So when intensity is 1 by 10 to the power minus 12 watts per meter squared, the pressure variation is about 3 times 10 to the power minus 5 Pascal. When it's about 1 watt per meter squared, the pressure variation is about 29 Pascal. And this gives pain to the ear. Have you ever been in a place where music is blasted at a top volume and your ear begin to reverberate? Man, it means that hair is having problem due to what it has had. So let's look at our attendance code, the first attendance code, so that we can fill in our attendance. Just a moment, I'm trying to get where the attendance is now. The attendance code, be getting yourself ready. Code 1. Okay. Just a moment. Attendance code 1. Attendance code 1, pardon me, is I will dictate and also write down QT, JFH, QT, JFH. I want us to attend to it now. Attend to the attendance code. Now, so let's take some few seconds to do that before we continue. Please attend to that attendance code, the first one. We then proceed. So as I said, intensity is defined as power per unit area, and we can see what could cause pain to our ears because of the pressure variation of about 30 Pascal. Invariably, we can say here that human hair can detect pressure fluctuation as small as 3 parts in 10 raised to power 10. We say that our hairs has an extraordinary sensitivity, but that's not the total picture. That's not the total story. I did say the last time that the hearing system of an elephant can detect. You know, I gave you an example of earthquake wave. Anywhere the earthquake operates. The one we hear about, I told us about certain part of the world that has earthquake every day, almost every minute. But the one you hear about, the recent one is in Indonesia or something like that, about 2 or 3 days ago. The one you hear about in the news is the one that caused destruction. And those ones that cause destruction will also follow with tsunami. But that's not where we are going. The point I'm making is the earthquake wave that is in the infrasonic region, not ultrasonic, that we don't hear, as sensitive as our ears are, cannot hear that, but the hearing system of an elephant can detect that. You see, an elephant that's big, but can detect the earthquake. So that's another wonder. That's why I said it's not the total picture. That's not the total story. It's not the total package, so to say. So now, the reason why our hearing is not in linear, it's not operating in linear mode. That is to say, if the intensity is then raised to say 10 decibel, as we see here, what do we then hear? No, so if the intensity is 1 times 10 to the power minus 11, you can see 1 times 10 to the power minus 10 is giving 0 decibel. I hope we're able to see that almost immediately using this formula. Log 10 of the reference I naught is always this, the threshold of hearing. That's I naught. And it is what you have in the denominator here. That's what you have in the denominator here. So it's quite easy to see that when intensity level is 1 times 10 to the power minus 12, when you put it here, when you substitute that here, and the reference is also 1 times 10 to the power minus 12, log that of that. When you know you have a ratio of log, what it translates into is 1, that's I minus I naught, the value, the log 10 value of it. That's what it translates into. And when you take the same value, when you take it from each other, it becomes 0 decibel. So you hear faintly, if at all you hear the intensity, the decibel level. Then let's say you just, by a factor of 10, just reduce by a factor of 10. 10 to the power minus 12, 10 to the power minus 11, you get 10 decibel. You can try it, plug it into the values, you'll see that. And that is why our ears don't hear in linear. One very light example that I'm going to give to you is the example of the politicians trying to do their primaries, and you hear on the social media recordings, they count 1, 2, 3, they go to a point, you just discover a jump. As a person, I didn't give it a serious thought. I just feel it's just, what do you call this? Skits. But it appears there is truth to it because it's been discussed on various national television. But that's on a lighter note. I'm not advising that we'll follow that kind of dishonest perspective. But all I'm trying to achieve, giving that example, is for us to be able to see that our ears do not add up in the linear or arithmetic progression. Just a factor of 10 reduction here gives us 10 decibel. Another factor of reduction here, 10, gives us 20 decibels. And by the time we reduce 10 to the power minus 10 to the power minus 4, that's around a reduction of 1 million reduction. Then you have 80 decibel. So if you calculate the percentage, what it means is 10 decibel, this 10 decibel is 10 times. It's 10 times more intense. 20 decibels is 100 times more intense. 100 from the reference. 10 from the reference. I hope you can see that. 120 decibels, which is the threshold of pain. This one is the threshold of pain, is 1 trillion times. The other one, this one, 80 decibel, is 1 million times. 1 million times. 1 million times. Meanwhile, the threshold of pain is 1 trillion times more intense than the softest sound you can hear. And how do we get to that? What makes it easy to see is the power of the logarithm. This logarithm is the power of the logarithm scale. So, don't forget this expression. Don't forget this expression too. This formula, don't forget, is important. This formula is also important, and you should know the application of the formula. Of course, we're going to demonstrate something similar to demonstrate that. Yeah, I'm hoping to see whether there are comments, whether you are following the class. I need 1 or 2 of you to just let me know whether I'm communicating with you with respect that communication is taking place. Communication is when I speak and you actually understand what is being said, and whether we have also attended to the attendance code, the first one. I want to give the other one now, because nobody knows when things can strike. So let's look at the second attendance code. Second code. I'm typing. Second code is ADB for you. ADB for you. Hello? Are we all together? Can you hear me? Can you read my charts? Can you hear me? Can you read my chart? So I need you to respond so that we can. So I need some kind of response from you, ladies and gentlemen. I need some kind of response from you. Can you read the chart? Can you hear me? So, let's look at an example. Let's look at an example. Hello, I hope you can hear me and read my charts. So, from the hearing threshold, the pain threshold, we should endeavor to operate within this range so that we avoid damage to our hairs. You can see that this 10 is actually a smart multiplier, intensity multiplier, which adds to the 10 decibel level. Now, so common sound levels. The common sound levels is crystal clear now that sound intensity is measured in decibels. It's measured in decibels. And like we have shown a table before of the speed of sound in different media, air, fluid, and solid. We showed that table earlier. So you also pay attention to this table. Typical intensity level for everyday sounds, ranging from faint rustling of leaves to the roar of nearby jet plane. If you have ever experienced taking flight, so that by the time you are going to the tarmac, you see those walking, this staff, the tarmac staff and what have you, putting something to their hair. That's hair protectors. It's not that they are listening to songs, like some of you walk around with headphones. No, it's actually to protect their hairs because the nearby jet plane has 150 decibels. Intensity level, 150. Go back. What our air can tolerate is 120. So over time, if you continue to work in that, exposing your ears, you become deaf. For that is part of occupational hazard. Rocket concerts, do we even measure those things when we in this country? Okay, let me zero down to our university here in OAU campus. I walk around and I see programs in amphitheater. Do we bother whether the intensity level is within the range of human hearing that will not cause pain, not beyond 120 decibels? So if you say education is costly, try ignorance. So at concert, it's set at within the range of the threshold. You may not know the value of subway. We don't have subway here, but we now have train that is working. But if you ever took a train, you see that the sound of incoming train, the noise is not very friendly to the ear at all, not very friendly. And you know one thing we do a lot in this country? Honking. Pressing the horn of a car, go to Lagos, go to Ibadan. You don't take consideration or cognizance of those who wear pacemakers. That is not really friendly to high level of intensity. It could cause collapse. So many of us, we cannot talk, we cannot hear until we shout at each other. So the noise pollution around us is the reason. That's the noise pollution around us. And when you do shout so that others can hear you, the vibration of your vocal cord is strained. You strain your vocal cord so that that vibration is beyond or above normal. And you look at compounding effect on our health. As I said, if education is costly, try ignorance. You may be certificated, but are you really educated? So in every traffic, you have 80 decibels, which is going to the region of 120 decibels. So in normal conversation should be around, can we talk in normal 50 decibels? How do we measure that? You can try that. What are other ways to know that if I'm speaking too loud? When you whisper, some people in the same room, they speak on phone, the other person doesn't hear them. The rustling of leaves is around 10 decibels, which is in the range of. So please take note here. Prolonged exposure to above 90 decibels can damage hearing. And if there's nothing you are taking away from this course, of course, you must pass this course so that you can proceed and do well. You also imbibe what is important. So when you are mounting a jet, an aeroplane, and you are not a worker just for a short time, for the little time that you are just climbing onto a plane, please put your hands to your ears. Cover your ears, the two. Otherwise, constant exposure to that will damage your hearing. And that gives you some element of sound hearing health. So let's look at an example to drive the decibel calculation to drive the point home. I do say this to students in class. What a teacher will do is not to give tough example, is to give very simple example, because life itself starts simply. But you will then begin to apply that simple example, build it up little by little to solve a complex problem. Of course, complex problem is an aggregate of simple example here and there that come together. So let's do a calculation of a decibel level from a given intensity. The question here says a loudspeaker producing sound with an intensity of this value, 5 times 10 to the power minus 4 watt per meter squared. So I write I, that is the I here. In the formula 10 log 10 I ratio I naught. And I naught is always 1 times 10 to the power minus 12 watt per meter squared. The question says, what is the intensity level in decibels? So this formula of beta becomes Andy, which is this formula. We now know I, which is this watt per meter squared. This is given. This is I naught. Substituting the values. And as we are doing the substitution, let me also give us the third attendance code. Let me also give us the third attendance code. And for us to take a bit of rest. I'm not reading anything from you, and I'm not really comfortable with that. Even though you, but I feel to have a feedback that the class is progressing, that I'm making PJ, PD, PJT, B. That's the third attendance code. Let's attend to that. And I will need you to respond to me that you are hearing me. Can you hear me? So I'm back. Yeah, thank you very much. I'm relaxed now that you can hear me. I can read that you can hear me. Something happened. You will get the slides. You will get the slides immediately after the class. Don't let me say immediately, because integrity says when you say something, you should live by that. You should live up to that. But the course coordinator or the course secretary will send us the slides. Yes, we can't hold on to it. You can't really see the screen if not zoomed. Let's see. Yeah, can you see it that way? Can you see the screen that way? Yeah. So have we substituted the values? What you need to do first, how you need to approach it. We substituted the value. When you substitute this, get the ratio log 10 of this minus log 10 of that, you can do that. You get the value of log 10, or you do the division first. When you do the division and you get log 10, 5 times 10 to the power 8. What is done here, please, you have to recollect the rules, the logarithm rules. When it's a ratio of A to B, it's minus in log. Log A minus log B. When it's A by B, is addition in log if they are in the same bracket. I hope you can follow. So what is done here is to get log 10 of 5, this is 5, and to get log 10 of 10 to the power 8. Log 10 of 5 is 0.699. Log 10 of 10 to the power 8 is 8. Other people may approach it differently. What is 5 times 10 to the power 8? You can put the value. 5 times 10 to the power 8 is 5. Then 8 zeros. Then you can get log of 8 zeros. 5 by 8 zeros. You still get, what you end up is it's 8.699. So when you then multiply 10 by 8, you get 86.99. 86.99 is what is roughly 87 decibels. Situate that answer to the range of pain and the reference range. The reference intensity is 1.0 times 10 to the power minus 12 watt per meter squared. That's the reference intensity, which is what we have here. Are we good with this? Are we fine with that? So, the next is to look at, now let us talk about how sound spread out in space. Let's talk about that. The same way we have wavefronts in water is the same way it is in sound, even though we may not be able to physically see it. As I'm speaking, my vocal cords are vibrating. That is why I'm able to produce sound. You have to agree with that. And that's why the sound I'm producing transmits energy to you. That is why you can also hear me wherever you are. Even though with the aid of, because we are not sitting before each other with the aid of devices that we hold now. I speak to a computer, you receive through your phones or other devices. But let it be within your medulla that sound spreads out in space. Look at the diagram. Look at this diagram. That's how it spreads out in space. And okay. Yeah, it spreads out in space. A small source like the one speaking to you or a small speaker emits sound in all directions. For some of you that are in the habit of doing skits or doing content, as you call it now, you hold small sound producer, you hold it and you move a little bit away from it. Why not sit very close to it? Because sound can move in space. And this sound is emitted in all directions equally, irrespective of whether you are sitting at an angle to it or directly in front of it, is the same. So it doesn't discriminate. When you sit very close to a speaker blasting music by the side, as long as you are close to it, you risk the damage to your ears. So this direction, as it is in this figure, are called wavefront, and they are spheres expanding outward. Spheres expanding outward. So the radial lines called rays are perpendicular to the wavefront. At large distances, wavefront becomes flat, forming plane waves. The rays are lined perpendicular to the wavefront. Because the same amount of power is spread over a larger and larger area as you get farther and farther away. As you get farther and farther away, the intensity drops. This is the source. As you go away from it, the value of the intensity reduces. Otherwise, or in other words, we say the decibel reduces. And why is it so? Because intensity with respect to power, look at this, has something to do with the square of distance. And that's also not linear. And it speaks to the reason why our ears do not hear in linear form. As I joke with us, just to drive the point home. It's not the kind of counting in the just concluded primaries of political parties, no. That they get to 50 and they say 100, 200, 300, no. But the reason for this we're giving to you is because of the R squared. Linear, it will be r raised to power 1. But non-linear, r squared. If the distance is 2, by the time you move another 2, 2 plus 2 is 4. 4 squared is different from 2 squared. 2 squared is 16. 4 squared is 2 squared is 4. Pardon me. 4 squared is 16. 4 to 16 is a lot of number. Is a big leap. So if you double your distance, and so what we are saying is because of the inverse square law. It is so because of the inverse square law. So if you from the source, density drops by a factor of 4, by a factor of 9. You see that? And when you are very far from the source, a small portion of that sphere looks flat. That's the kind we're having around here. We look flat. Those will be called plane waves. That's the kind of example that can be found in, for example, when light from the sun reaches the earth, the wave fronts are essentially flat. So please, this expression, that's another expression, is important. It is to say that I is proportional inversely to r squared. All other things you see here, average power, 4 pi, are constants. This is constant, 4 pi is constant. But the moment this changes, it changes the whole equation. And one will try to drive this home by an example that we should consider next. That example says, a point source emits sound uniformly in all directions with power. Please pardon me, this is power is 50. Power is 50 watts. Find the intensity at a distance. R is 5, pardon me again, meters. Are we together? I told you 4 pi is constant. R changes the whole thing. So when you substitute, power is given 50 watts. R is given as 5. They are all in the unit. It doesn't need any conversion. When you want to solve a problem, you need to look at whether there's need to convert. Maybe you have unit prefixes and what have you, but this one is straightforward. We do that a lot, giving simple example. So intensity from that calculation, when you do it and you do it well, is 0.159 watt per meter squared. And you know why it is so? Power is watts, R squared is meter squared. So that's why you have the unit watt per meter squared. Do I have anybody who's tried it and is getting something different? I need the class to talk. So, having done that, we feed that in. The intensity 0.159, we fit it in into, don't forget that I naught always, which is I naught in this expression, this is I, which we got here. I naught is always 1 times 10 to power minus 12 watt per meter squared. That's the reference intensity. That will raise its head all the time. For us to be able to get the decibel level, which is beta equals 10 log 10 I over I naught. And when you do it well, you should get about 112 decibel. What's the highest that will give us a pain in our ears? Is 120. And this is nearing, this 112 is nearing that. So it's not just about solving the problem. We should also know the implication of the answers that we get. That is one major difference between physics and mathematics. Mathematics will solve some problems. The language of physics is mathematics, but we must physicalize, if there's any English like that, we must physicalize our own answers as physicists or people learning physics. 112 decibels situated. At 112 decibel, this is well above the 90 decibel threshold for potential hearing damage. Don't forget, let me quickly go back to the table. Table says threshold of pain. It means the pain has started before that. But if you continue at 120 decibels, probably go deaf. You know, some people were born not with deafness. I know a couple of people like that. Or they acquire, if there's anything like that, deaf, unknown to them, exposing the ears. So, ladies and gentlemen, watch the headphone, watch the volume you put. You are impressing no one. You're actually hurting yourself. If you put a headphone and somebody walking by your side is hearing what is being played on your headphone, you are actually hurting your ears. So if people don't shout, you won't hear them. And there will be a limit to how people can shout at you. They will not also want to damage themselves. So 90 decibel threshold for potential hearing, prolonged exposure to which can damage the ear. So that is that we are to consider today, but let me quickly run us through what we have been able to do. We have looked at intensity definition. We have considered decibel scale. And it is, to recap, we should know that this decibel scale is logarithmic in nature. So it is not linear. Excuse me. A factor of 10 reduction means 10 times from the reference. Another factor of 10 means 100 times. That's the log. 100 times in terms of intensity. So we also looked at common sound levels from 0 decibel to 120 decibel threshold of pain. And that when you are stepping on top of a plane, some of you will very soon do that from time to time, or you are in a train station, please try to, for the moment, try to put your hands on your ears. We have also solved 2 problems. The last one is what we did now. And you should also know that inverse square law is about the intensity being inversely proportional to the square of radius. So 2 problems have been solved. We have, decibel intensity, and we also look at power calculation. So I is P over A, beta is 10 log I over I naught, log of the ratio times 10 to the power whatever. So please, as part of something that we should ponder over, just to aid your private study, what's the loudest sound you've ever heard? What's the loudest sound you've ever heard? The attendance form is not working. How do you mean? How do you mean not working? So, another thing that for you to ponder over, if you move from 5 meters to 15 meters from a speaker, by what factor does intensity drop? But just hold on for me a moment. Hold on for me a moment. Let me attend to the attendance matter. Attend to the attendance matter. Hold on. So we hear you in terms of the attendance form. We'll undo that later and we'll get back to you. Please, class, we meet on Wednesday. And by that Wednesday, we will be talking about, let me prepare our mind, Doppler effect. Ambulance, think about it. Making sound. The farther you are away from it, the less troublesome, in quote, if you permit me to use that. The more you are close to it, the more it becomes irritating. And it's nothing other than the change observed in observed frequency due to relative motion between a source and an observer. So we'll look at that next class. Enjoy the rest of the day, ladies and gentlemen. See you on Wednesday. Thank you, and thank you very much.